Okay, Trig students, this is section 4.3, and we are reviewing log functions, both basic logarithmic functions and natural log functions. So I want to review a couple of things first. Your basic log function, log base A of x equals y. That's kind of how it's stated. That is the same thing as writing it in exponential form when it looks like this. This would be a to the y power equals x. Okay, just want to remind you the best way to kind of think about log functions is to rewrite them as an exponential function. Okay, logs are actually the inverse of exponential functions. Okay, so just as an example here, if I had log base 2 of 8 equals x, okay, well, how would I go about trying to solve that? Okay, rewrite it in exponential form. Okay, rewrite this in exponential form, it would look like 2 to the x equals 8. Okay, and so then we know pretty easily that 2 to the x would equal 2 cubed, so x equals 3. Okay, 8 is 2 cubed. So if we can equate two quantities with the same base, then we can set their exponents equal to each other. So we know that 2 cubed equals 8. Okay, just wanted to remind you guys of that. Now, something that some of my students have liked to do over the years, and I think I showed you this last year, is kind of draw a heart to remember what goes where. So 2 to the x power equals 8. Anyway, that's a little trick that some of my students over the years have liked to use. But 2 is the base, okay, when you rewrite it in exponential form. The littlest number in logarithmic form is kind of like almost the biggest number in exponential form. Now, I want to just touch on the fact that logs and exponential functions are inverses of each other. Okay, so if we had the graph of y equals 2 to the x, okay, y equals 2 to the x. Well, that exponential function we know goes through the point 0, 1, most of them do. And then if I plug in a 1, I get a 2. If I plug in a 2, I get a 4, so on. If I plug in a -1, I get a half, a -2, I get a -4. So here's what my exponential function looks like graphed, right? Your x-axis is your horizontal asymptote, okay? Conversely, if I am graphing y equals log base 2 of x, okay, this, you're literally taking the inverse, okay? This is going to be a half, this is going to be a fourth. So give you this here. This is what your log function would look like. These are inverse operations of each other. Okay, so if you remember, inverse operations reflect about the line y equals x. Okay, so the point, this point here on my exponential function, that was the point 2, 4. On my logarithmic function is the point 4, 2. Okay, the point on my exponential function, that is 1, 2. On my logarithmic function is the point 2, 1. Okay, they are inverses of each other. So again, they are going to reflect about the line y equals x. Okay, now we have some properties of logarithms, okay, that I want to review with you. Again, I know none of this is new, but it's been a while. So properties of logs. The first one, if you have log base a of 1, it equals 0. It does not matter what your base is. And think about that. Anything to the 0 power equals 1. That's what we're getting at, right? So essentially what this is saying is anything to the 0 power equals 1 if I write it in exponential form. Okay, so that rule's pretty easy to see, I think. Log base a of a equals 1. And again, that makes sense if you rewrite it in exponential form. A to the first power equals a. Well, of course it does. Okay. Next log rule, log base a of a to the x equals x. Okay, it's almost like you can cancel out the log base a and the a, and then the little x in the exponential spot on the left just kind of drops down. And again, if you rewrite it in exponential form, of course that makes sense. A to the x equals a to the x. Okay. And then the last one, if you have a to the log base a of x, that just equals x. Okay, this one's a little harder to see, but again, it kind of is in the same vein as here. It's almost as if these two things cross out and it leaves you with this. Same thing here. It's like these two things cross out and leaves you with this. Okay, same thing. Okay, so basic properties of logarithms. We also have natural logs. Okay, I want to remind you that log base e is the same as ln. It's the natural log. Okay, so if you just see an ln, you could literally replace it with log base e. Also, I want to remind you that if you just see a log with no base, it kind of defaults, it assumes it's log base 10. Okay, it defaults to 10. If they don't give you a base number, it defaults to 10. If the base is e, they usually write it as ln. Okay, so wanted to remind you of that. So quickly, let me kind of go over the natural log properties with you. And very similar, I'm not going to spend a whole lot of time here, but natural log of 1 is 0. You can kind of see how that goes hand in hand. Natural log of e is 1. Ln of e to the x is x. Again, if you want to think of it this way, it's almost as if those cancel out. Okay, and then e to the ln of x also equals x. And again, you can kind of think of it as the e and the ln canceling out. Okay, so the same properties that we have for regular logs also work for natural logs. Okay, wanted to kind of touch base of those before I move on to some of your homework problems, because I would really like for you guys to get going on this. It's kind of a long section, and the more we can get working ahead, then the less rush we're going to be before Christmas to get through everything. So let's look at homework problems. So homework problems from WebAssign. It says log x is the exponent to which the base 10 must be raised to get, that's going to be x. All right, so we can complete the following table for log x. I'm not going to spend a lot of time on this, but if we have, remember what your basic log is if they don't show it. If I'm replacing, if I've got log of 10 cubed, well, that's the same thing as log base 10 of 10 cubed. Okay, well, what happens then? Again, according to my property, those kind of cancel and I'm just left with 3. Okay, so you're really just left with the exponent. Okay, not going to spend a lot of time there. Number 2, I think it's fairly self-explanatory too. the function f of x equals log base 4 of x is the logarithm function with base 4, okay? So f of 4, so if I plug 4 in, what they're saying here, f of 4 equals what? So if I have log base 4 of 4, what does that equal? It equals 1. 4 to what power equals 4? Okay, f of 1, if I have log base 4 of 1, okay, sorry, I lost my place. Log base 4 of 1, what does that give me? Well, 4 to what power? Again, if you don't see that, rewrite it in exponential form. This is essentially 4 to what power equals 1? Well, that's got to be 0, right? Anything to the 0 power equals 1. If you have this one, I'm not going to have a whole lot of room underneath, so let me kind of move down. So here you'd have log base 4 of 1/4 equals what? Well, again, rewrite this in exponential form. This is 4 to what power equals 1/4? Well, how do I get from 4 on the top to the 4 on the bottom? That means x would have to equal -1 to be able to flip it down. Hope you guys are seeing this. Okay, I'll let you do the next two. But that's what they're talking about. They're rewriting it. Log base 4 of 1/4, log base 4 of 4, log base 4 of 1, and you have to fill in the answers there. Okay. Let me clear this out and then we'll keep going. So convert the following to logarithmic form. Okay. Again, this becomes your base. Okay, it is your base, and exponential, it becomes the base, then logarithm too. So it's log base 7 of 2,401 equals the exponent. In my mind, the way I kind of remember these is the little bitty exponent in exponential form becomes the big answer in the logarithmic form. It's almost like they swap places. And the big base in exponential form becomes the little bitty base in logarithmic form. So it's almost like they switch importances, if that makes sense. But that's how you would rewrite that. So 7 to the 4th, again, you could use that little heart trick thing. 7 to the 4th power equals 2,401. Okay, but that would be logarithmic form. And so converting that to exponential form, I think that's a lot easier to see. Again, 7 squared equals 49. Okay. Moving along. I'm going to let you guys have those. Express in exponential form, I think you can do that as well. Same thing, although, actually, let's look at part B on this one. I'll do both, actually. Okay, so here we have an exponential form. Again, this becomes your base. It is your base, but 5, this, the number all by itself becomes your little bitty exponent. So 5 to the -3 power equals 1 over 125. Okay, and remember, when you have a negative exponent, you have to move it down. So that's where they get the 125 on bottom. This one, again, is 8 to the 2/3 power equals 4. Now, just for kicks and grins, I want to remind you how they get that. Okay, 8 to the 2/3 power, I would split that up into 8 to the 1/3 power squared. Okay, I can split the 2/3 up into 1/3 squared because remember your exponent rules. A power raised to another power, you multiply. So the 8 to the 1/3 power is like the cubed root. So that is 2 squared, which is 4. Okay, just a reminder. Now they get into some ln stuff. So ln, remember, is base e. Okay, so it says express the equation in exponential form. This would be e to the 6th power equals x plus 5. Okay, same thing here. E to the 7th power equals x minus 9, and so on and so forth. Okay. I printed these off so I know how far down I want to scroll, but a lot of these are just converting. So let's move on to some of the ones where we actually have to solve. Whoops. I was trying to scroll and it made a mark instead. Okay, so now we're evaluating the expression here on 11. Okay, if you remember some of those log rules we just went over, okay, honestly, this is like the log base 6 of 6 cancels and you just end up with 7. Okay, if you wanted to like rewrite this in exponential form, it'd be 6 to the x equals 6 to the 7th. Well, then of course, x equals 7. Okay, on part B, again, rewrite it in exponential form. So like I'd be kind of finishing the equation like this. Log base 4 of 64 equals x. So then to rewrite it, you're asking yourself, 4 to the x equals 64. Well, 4 times what power equals 64? Well, obviously, that is cubed. And then same thing down here with this one. You're asking yourself, 5 to what power equals 125, which is obviously also cubed. Okay, so you're going to have to rewrite those logs in exponential form sometimes to kind of see it. I have no idea why that just popped up. Okay. Same thing here. 2 to what power equals 16? 9 to what power equals 9 to the 16th? Again, you can kind of view it, in my mind, I kind of almost view it as if those cancel. Your answer would just be 16. This one again is 2 to what power equals 1? Well, that's going to have to be 0. 0 is the only exponent that gives us a 1. So a lot of these are pretty straightforward. Now into some of these weird ones. If you remember here, those rules that I went over, again, e to the ln cancels. You're just going to be left with root 5. Same thing here, e to the ln 1 over pi. And remember here, if you don't see a base on the log, it's assumed to be base 10. So once again, those would cancel and just leave you with 18. So I think that's pretty straightforward. Yeah, all of these, I think now that we've kind of covered the high spots, I think you're going to be okay now that you kind of understand again how logs are done. These, they just want you to use a calculator, okay? Here, fill out the table. Okay, now we're getting into the graph. So remember what I said earlier about graphs, okay? Now, one thing I do want to talk about, if we have, just in general, if you have the graph of a log function, unless it's been shifted, it's going to go through the point 1, 0, okay? So if I had log base 2 of x, it would look like this, okay? Now, what if I had log base 2 of x plus 2? Again, what does that do? This shifts the whole graph up to. We've talked about graph transformations many, many times. If you have a plus or minus hanging out the back of a function, it shifts it up or down. Plus is up, minus is down. So in this case, if I were graphing this blue log base 2 of x plus 2, it would literally just move the whole graph up 2 places. So instead of going through at 1, 0, it would go through at 1, 2, and this would be my graph of my function. Okay, now what if I had like log base 2 of x plus 2 and it was included in the function? Okay, if it's included in the function, remember it's a left or right shift and it's kind of backwards. Plus 2 would actually mean left 2. Okay, so if it's included in the function, it's left or right, and it's kind of backwards as far as the sign goes. So instead of going through the point 1, 0, it would go through the point negative 1, 0, and it would look like this, or thereabouts. Its asymptote, its vertical asymptote, instead of being the y-axis, would be the line x equals negative 2. Okay, it just shifts left 2. And that drawing's not very good. I kind of had it going to the right a little too soon, but you get the idea. Okay. Also want to remind you that, actually, let me erase this and draw again. Want to remind you that when you shift about the x-axis versus when you flip about the y-axis. So again, let me start with the graph of y equals log base 2 of x. And again, I graphed it at the very beginning of this video, but it looks sort of like this. Okay, I'm just kind of keeping a rough sketch because that's all you really need. What would change if I had y equals negative log base 2 of x? What would change in my graph? Well, it literally flips about the x-axis. Okay, so this one would be looking like this, or thereabouts. Okay, now what happens if I put the negative? What happens if I'm graphing this sucker? If I have log base 2 of negative x, what happens if I put the negative inside the function? Then that is a flip about the y-axis. Okay, so if the negative's out front, it's a vertical flip, up or down. If the negative is included in the function, it's a horizontal flip, left or right. So in that case, instead of going through the point 1, 0, it would go through the point negative 1, 0, and it would look like that. Okay, so I just kind of wanted to show you all of these on the same graph so you can kind of get an idea. And again, if you had a -3 hanging out the back of the whole function, the whole thing shifts down 3. If you had a, I don't know, -3 inside the function in the parentheses with the x, then it'd be a right shift 3. So all the graph transformations that we have already learned over the years still hold true, even with logs. Okay. Okay. Honestly, I think that's about it. I think that's enough to get you going good on these. I know logs are kind of scary because we don't use them all that often, so sometimes it's kind of hard to get back in the swing of things. But I think you got this. Some of them ask for local max or local min. There's a couple of word problems at the very bottom, but there's watch-its for both of those, and they're super easy. It's just honestly a calculator exercise. Don't forget when you put rates in to convert them to decimals, okay, and percentages as well. So at the bottom of your assignment on like problem 29, they want to know carbon dating, and they say there's so much percent of carbon left, and so you have to convert that to a decimal, okay? So anyway, I think that's good. If you guys have any questions, shoot me an email and we can jump on a Google Meet and I can help you. All right? Good luck.